Now we're going to talk about what are called partial sums of a sequence. We're going back to sequences here. So suppose we have a sequence with the terms A1, A2, A3, A4, so on and so forth. We can form what are called partial sums, denoted S1, S2, S3, so on and so forth, for the sequence as follows. S1 is just the same thing as A1. But S2 is what we get when we add A1 and A2, the first two terms together. S3 is what we get when we add the first three terms together, A1 plus A2 plus A3, and so on and so forth. So Sn denotes what we get when we add the first n terms of the sequence together. When we add terms of a sequence, in math we say that we get something called a series. I'm not using the word series a lot in these videos, but that's the title of this section of the book, and that's where that word comes from. Adding the terms of a sequence gives us what's called a series. So let's go ahead and do an exercise here. Exercise 1. Just here we're given an equals 8 plus n minus 1 times 0.5. So that's an arithmetic sequence with a1 is the 8 and d, the common difference, is 0.5. We want to find the first four partial sums for this sequence, and we're just going to figure those out right here. So let's see, the first is S1, which is equal to A1, and so that's just 8 here. It's the same thing that we get if we plug n equals 1 into the formula, because 1 minus 1 will be 0. We don't have to add on a 0.5 term, we just have 8. So there's the first partial sum. That was easy enough. S2 is going to be A1 plus A2. So we're going to take that 8 that we already figured out, and we're going to add A2 to it. Now, if I go up to the formula, A2 is what I get when I take 8 and add on 2 minus 1, or that's going to be 1, times 0.5. So it's going to be 8 plus 1 copy of that 0.5. And so when I add all this up now, A1 plus A2, I got 8 plus 8 plus 0.5. So that's 16.5. That's call my second partial sum. S3 is going to be A1 plus A2 plus A3, which is 8 plus, we already figured out A2, 8 plus 0.5, plus, now I'm going to add on my A3 term. A3 is what I get when I set n equal to 3 in the formula. I'll get 8 plus something, right? 3 minus 1 is 2. I get 2 times 0.5. And now I'm going to add all this up. Now, 2 times 0.5 is just 1 whole. So I have 8 plus 8 plus 0.5 plus 8 plus 1 whole. That's going to be 3/8 is 24, 25.5, 25.5. And S4, A1 plus A2 plus A3 plus A4. Now, if you see the pattern here, you might recognize that really to get S4, I could even take my answer for S3 and just add an A4 onto it, right? We keep adding like one more term of the sequence on to get the next partial sum. But I'm going to write out the whole thing here underneath the S4 expansion. A1 was 8. A2 is 8 plus just 1 copy of 0.5. A3 was 8 plus 2 copies of 0.5. And now I'm going to put my A4 term, which I can get from the formula, but I can also just see the pattern here. It's going to be A8 plus 3 copies of 0.5. And just to make sure this is clear, I'll write it 8 plus 0.5 plus 8 plus, this was 1.0, plus another 8 plus 3 copies of 1.5 of 3 copies of 0.5 is 1.5. So when I add all this up, I got 4 eighths is 32, 33, 34, 35. I think I got 35 even, so I'm going to write 35.0 just to stress that. There's the fourth partial sum. So that's the idea of partial sums. Okay, so we could write more, but they only ask us for the first 4 partial sums, and we got it. Okay, let's continue. What we're going to do is we're actually going to derive a more general formula now for finding the partial sums of an arithmetic sequence. And so I'm going to, in this case, I'm not going to work with a specific example. I'm just saying let an equals a1 plus n minus 1 times d denote any arithmetic sequence where a1 and d are real numbers. So a1 stands for the first term, d is the common difference. And so we're going to try to come up with a formula for this s sub n, which is a1 plus a2 plus a3. Now, there's no way I can say, without having a specific value of n, where to stop other than doing something sort of like this, writing plus dot 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 plus an. So that's my way of saying I'm adding up the first n terms. Now, if we use our formula, we can express Sn as what I get when I plug in 1 for n. And of course, when I plug in 1 for n, I will just get a1 plus 0 times d. For a2, I will get a1 plus 2 minus 1 is 1. 1 times d is d. I just get a1 plus d. For a3, when I plug in 3 for n, I will get a1 plus 3 minus 1, or 2 times d. And basically what's going to happen is I keep adding on a larger and larger multiple of d all the way down the line till I get to an, which in general I can say is a1 plus n minus 1 times d. Now, what I'm going to do is I'm going to write Sn again a different way. And instead of starting with a1, I'm going to describe Sn, the same partial sum, starting with the nth term, a sub n, and I'm going to work my way backwards. So I'm actually turning the terms around in order. I'm going to put an, then the one before, then the one before, and I'm going to end up at the end with a sub 1 all the way on the right-hand side. And I'm going to describe this, not using the formula so much, but the idea, what would happen if I work my way backwards through the terms of this sequence? Because I know as I go forward, I add on d, excuse me, then I add on another copy of d, and another copy of d. If I go backwards, I'm going to take an, and I'm going to subtract a copy of d from an. So the term just before an would be an minus d. And if I go backwards again from that one, I would subtract another copy of d. I get an minus 2d. So while going forward through the terms, I keep adding a copy of d. When I go backwards through the terms, I keep subtracting a copy of d. And I go all the way down the line. And now this last term is just going to be a sub 1, but I'm not going to write a sub 1. I'm going to describe it from starting from a sub n. I take a sub n and I subtract a whole bunch of copies of d. I'm going to subtract n minus 1 copies of d to get back to a sub 1. So we describe that Sn a totally different way, sort of from a sub n's perspective. Now the weird thing I'm going to do is a funny little kind of trick step. I'm going to add these two lines together. So I'm going to add on both sides of the equation Sn plus Sn so this version of Sn plus that version of Sn. I might even draw a line underneath to kind of make it look like I'm doing addition. Well, I have a1 plus an. I'm going to write a1 plus an, and I want to put that in parentheses. And then I'm going to look at the next couple of parentheses here. I have an a1 plus d and an an plus d. So I got a1 plus an, but the plus d minus d, when I add them together, they cancel out. So from these two parentheses, when I add them, I just get an a1 plus an. And from the next pair, a similar thing happens. I get a1 plus an, and I got a 2d minus 2d. This almost seems like magic, like I'm pulling a fast one on you. I would say, can you really do that? And we can. And that's going to happen all the way down the line, even down to this last term that looks so messy, because the plus n minus 1d and the minus n minus 1d, when I add them together, are going to cancel out and drop out, and I'm just left with another a1 plus an over and over again. So what we have here is, look at the same thing added to itself over and over n times, right? Because there were n terms in our original partial sum Sn. This left-hand side, Sn plus Sn, I can rewrite that as 2Sn, 2 times Sn. And the right-hand side, because I have that same quantity, a1 plus an, n times, I can just say it's n times a1 plus an. And so this long sum now I have expressed in this much more compact form. If I divide both sides by 2, I'm going to get back to Sn all by itself on the left, and I have Sn is equal to n times a1 plus an all over 2. And that's our formula that we were after. This is our formula for the nth partial sum of an arithmetic sequence. And I just want to make, oops, sorry, I guess I got off the edge. And I just want to make one observation here that one way I think of this formula is I kind of think of it as Sn is equal to n times a1 plus an over 2. That's equivalent. So it's like n times the average of a1 and an. It's like the average of the first and last term in the partial sum times n gives you that sum of those terms. Now let's just apply this to a problem. So let's go just a little bit further. One exercise here. Maybe I can keep my formula right above the page here. Let's actually do exercise 2. Let's find the 20th partial sum of the sequence defined by an equals 8 plus n minus 1 times 0.5. That's the exact same sequence that we were looking at in exercise 1. So maybe that's worth just writing down here, same sequence as exercise 1, and it is arithmetic. And so our answer here is going to be, all we want is S20. And now, again, I could actually calculate 20 of these terms and add them together. That's not, just be a bit tedious. I'm not going to do that. What I'm going to do is I'm just going to use our formula for Sn. It's n times a1 plus an over 2. So that's 20 times a1 plus a20 over 2. So what is that? That's 20 times a1. I know my a sub 1 is going to be just 8. If I plug in n equals 1. a20, I gotta figure out what that is. And so let's see here. Can I just do that on the side? A20 is going to be 8 plus 20 minus 1 times 0.5, or 8 plus 19 times 0.5, and I think that's going to be 8 plus 19 times 0.5 is going to be, I think that's 9.5. And so when I add 8 plus 9.5, I got 17.5. There's my 820. So I'm going to plug in here 17.5, and I still got to divide by 2. So I have 20 times 8 plus 17.5. That's 25.5 divided by 2. Now when I cancel here, I only have to divide by 2 once because I'm multiplying, and I get 10 times 25.5, or 255. And that's our sum of the first 20 terms of the sequence that's given. So we're going to stop here and talk about geometric sequences in the next video.